Hello everyone, and thank you very much for joining our live event today. Today I'm here with Dr. Oliver Coulert from SYSGO and Dr. Matt Grum from Rapita. We're going to start with Dr. Oliver Coulert from SYSGO. He'll have the first section and we'll be discussing the general challenges of using multi-core processors for safety critical avionics projects. Oliver will also introduce the PikeOS operating system and describe the multi-core mitigation system that it does include. Then Dr. Matthew Grum from Rapita will be digging deeper into the challenges of multi-core timing analysis and the guidance that needs to be followed. He'll introduce the MAC178 solution that Rapita offer and how this in turn can be used to verify the effectiveness of the PikeOS mitigation mechanisms that Oliver outlined earlier. After that, we'll have a 5 to 6 minute not live demo, a pre-recorded demo in fact, based on the NXP T2080, and that'll examine real data from a PikeOS and RVS integration. So I'm going to pass over now to today's first presenter, Dr. Oliver Coulert. Oliver is head of the Innovation Lab at SYSGO and is an expert in DO-178C verification and certification. Over to you, Oliver.
Good afternoon. I'm Oliver Coulert from SYSGO, and today we will talk about RTOS and RTOS challenges in avionics, especially with multi-core processor setups. So let's start with the company SYSGO. So we are alive since 1991 and started as a service company in the embedded market. One of our first products, which arises from this, was a Linux distribution, Avionics, and very soon we were also active in avionics and were the distributors of real-time operating systems dedicated to the avionic markets. And in 2003, we came up with our own operating system, which is a hypervisor and real-time operating system. Since 2012, we are part of the Thales group, but we did not lose our identity, which means we are still available under SYSGO labels and email addresses. So our products are the operating system I mentioned before, which is called PikeOS. Actually, it's now a family of operating systems because we now support big systems. So this is something which we did from the very beginning, which have a memory management unit. And recently, we even support smaller systems which only have a memory protection unit by still providing the separation and time partitioning approach. The other operating system is our Avionics, which is an easy to configure and to set up operating system. One of its unique points is the so-called system configurator, which helps to set up an entire system. Apart from that, we can build you board support packages on all our supported architectures. And when it comes to certification, we support you with our certification kits, which provide documentation and services around. And finally, we also offer training, consulting, and whatever you need to get your product into the market. So where are we located? So first off, this is where our operating system came from, is the aerospace. And PikeOS is an operating system which, first of all, is compliant to the ARINC 653 standard, which is well known in the avionics and integrated modular avionics markets. Then we are in defense, automotive, so we have several solutions and products here. And in railway and transportation, since we are talking about multi-core here, actually PikeOS is the first operating system that achieved a SIL4 level. We also provide solutions for industrial, and most recently we started some approach into the medical market. So We are both in the civil aerospace. That means that we are following the DO-178 certification, and our operating system, or we will come soon to this, claims to be CAS 32A compliant, or how Matt will explain later, the following up, which is the AMC standard. One of the planes we are in, for example, is the Airbus A350, and we are also in other airplanes. In this case, we are providing solution also for real-time networking, which are compatible to the AFDX standard from Airbus. For defense, we are in, for example, the A400M. This is where we built the Workmaster solution controller in the background, which is a little computer which controls the hangar of the airplane and the cargo door, and also has some communications to the cockpit. Next slide. So this is a list of our customers. Of course, Thales is also one of our customers. We are also in the space business with them, and we have many good relations to Airbus, Boeing, and all the other companies listed on this slide. So I will now talk about our real-time operating system, PikeOS. PikeOS follows the ARINC 653 standard, and the ARINC 653 standard comes up with something which is called resource and time partitioning. That means that each application is isolated to each other by strict partitioning in terms of spatial and time. And we have a little bit widened that philosophy and do not only support Apex applications. Apex is the API of the ARINC 653 standard. We do not only support ARINC 653 applications, we allow whole operating systems to be separated from each other. In extreme examples, that could even be a full Linux operating system or a, let's say, limited POSIX environment, or our PikeOS native and Apex things. This whole thing allows to build phase-compliant systems. In terms of the operating system, we can run the operating systems both hardware virtualized as well as para-virtualized. One of the most important use case here is the so-called mixed criticality. That means that you can run applications with different safety dull levels at the same time, and making sure that no lower level, the safety level has an impact on the higher level one. Also, we are a European company. That means that we are ITAR free, and everything is hosted within our development IDE Codio, which we'll see a little bit in the demonstration later. So in a nutshell, we support hard real-time. Hard real-time can be priority or time sliced. In the avionics, we usually have strict repeated time slicing. We provide safe and secure virtualization, mixed criticality, and multi-core. Our operating system, PikeOS, usually is run in an SMP setup. That means that there is only one instance for multiple operating systems. When it comes to PikeOS for MPU, we usually use an AMP setup, but this is only due to the non-existent cache coherency. So in theory, PikeOS for MPU could also run on SMP system, but in this case, we have to totally disable the caches, which is not very performant. Due to the virtualization and abstraction levels, we are very portable, and you can reuse existing codes and should separate it from the other applications very easily. And as mentioned before, we already have a multi-core certification for SIL 4, and with PikeOS 5, we go even far beyond that. Yes, certifications. So in DO-178B, which is the civil avionics standards, we can go up to DEL-A. For industrial certifications, we have SIL 3 and 4. For railway, SIL 4, even with multi-core. And even in the automotive, we go up to ASIL D, which is also the highest level. Almost everybody of our engineer already was involved in certification projects. So when it comes to certifications, you always have the issue that you don't know what is actually being already certifiable. So in case of PikeOS, what we provide to you is the PikeOS microkernel, which is extremely small. It's about 4,000 lines of code. And the PikeOS system software, which already runs in user space. And this one passes the containers, which might be ELF files or other files, loads them, initializes the partitioning and starts the system. This is also pre-certified and certifiable and part of our certification kits. Also, the architecture support is pre-certified. Currently, this is x86, PowerPC, and ARM. What usually needs to be certified in the context of the project is the PSP support. Also, for very limited number of boards, we already have the certification artifacts available for the platform support package. When you run an operating system or an execution environment, this is usually being certified in the context of the project. So realistically, nobody will really certify a Linux operating system. And in case of mixed criticality, this will run at lower levels, maybe DEL-C or DEL-D. But we have certifiable APIs, for example, our POSIX environment, our certifiable math library, or our certifiable IP stack, and also we have a certifiable file systems. These can be used in the context and your application, and because of their small size, it is quite usable in the context of higher level safety projects. The POSIX currently isn't certifiable at the highest level, but the execution environment of our PikeOS, native PikeOS, which is a very limited C environment, actually can be certified to level DEL-A, and in the past with PikeOS 4, we already did that. In case of avionics, civil avionics, the standard is the DO-178C. And usually what you cannot do is pre-certify software. So that's why I usually said certifiable. But since we have the certification kits and all available documents, and even the traceability to your application is prepared, the certification of the entire system should be quite straightforward. Another important topic is when it comes to tool qualification. So since this is a virtualization environment, we of course need some metadata about the size of the partition, the time partitioning scheme, and the memory allocated to each partition. So what you usually do is to generate a configuration file in XML. Of course, we have graphical editors for that. And this XML file is then converted into a binary artifact. This binary artifact is then loaded by the system software. But every little change you would do on the XML file would result in a completely new re-evaluation of the binary. So that is why all our tools are validated. That means that you can do the verification and validation on configuration in XML level, which makes recording changes to the files pretty straightforward. So with PikeOS 5, we've even gone a little bit further, especially on multi-core. So we extremely have improved and improved multi-core handling and reduced the interference between cores and have improved the performance, scalability, and determinism of the entire system. So the problems that you have in, or let's say the problem that the safety industry currently has is that they started the single core processors, and now multi-core processoring are moving into the embedded market. This is a little bit a problem to the safety standards, because for now they didn't allow multi-core, and there is this new CAS32 standards, and this CAS32 standard now allows, under certain circumstances, to use multi-core in safety and especially in avionics. So what is the problem? The problem is that you need determinism. And determinism does not mean that an algorithm provides the same output based on the same input. It also means that the algorithm is finishing in its allowed time frame. With PikeOS, you can set up time slices and assign them to applications. But how you can make sure that an application does finish within its time life, and this is what you need to do. It's called the worst case execution time determinism. In the past, this had been done with single cores, and you had to consider the number and bandwidth of interrupts, the scheduling behavior, the priority settings, and the memory controller and bus access, as well as the cache settings, which means when you access memory, the hardware plays an important role in the time that your algorithm actually needs. The problem is complex, but in the past, the industry has learned to solve it by usage of static and dynamic code analysis. When you have multi-core, the problem gets out of bounds because you have interference between the processor cores. That is because most multi-cores are implemented for average case timing and not so much for worst case. Even if this situation is rare, it may only happen once to cause a problem when a plane is in flight. So what do you need to look on the hardware level? So these are shared case, memory controllers, I/O, and anything that limits the bandwidth of the application to interact with its I/O and memory. As we will see, that these problems can be solved by cache partitioning and bandwidth monitoring. So here's a small table with some examples which can happen, which is the source and how to mitigate the effect. So on hardware level, one of the prominent things, except for example, bus controllers, is shared cache. So in this case, we are talking about L3 or L2 cache, which is being shared between the cores. Then sometimes if multiple applications go into the kernel at the same time, you have to make sure that inside the kernel there are no locks. And finally, on application levels, that the access to shared resources is coordinated and set up in a way that it does not affect the overall performance and the worst case for each application. So we divide those problems into hardware-related things, application-related, and OS-related. Let's start with the hardware-related issues. So you can solve these things with cache partitioning and bandwidth monitoring. So cache partitioning is a software measure to mitigate the contentions, and this is done within PikeOS 5.0 by partitioning the cache via the PSP level on each platform. This needs support from the hardware and needs to be clarified by case, but on most PowerPC and ARM processor, this is available. And when it comes to RISC-V, this already is in by design by most RISC-V platforms. When it comes to applications, the advice to the customers on the architecture is to group critical applications with each other and let at the same time on multiple cores and run the non-critical applications also in parallel on different cores and do a cache invalidation in between them. So let's look at the examples. Here we have 2 cores in the time partition window tau 1. We run a non-critical partition and an application with a high impact on the cache. Afterwards, we do a cache invalidation, and then we run the critical applications in parallel. And from those, we know the exact behavior because those have been certified and investigated that they don't access the bandwidth or the resources or shared resources in an unwanted way, so that we don't have any interference between those applications at runtime. And the last one is operating system. So what we changed in PikeOS 5.0 is a way better resource locking. And this is called fine-grained locking. So on the left side, you see the standard behavior of older operating system and versions of PikeOS which were below 5.0. In this case, we have application A and B, and they are doing both syscalls. And in the very moment that syscall A is being processed, if application B now wants to execute a service, it has to wait until application A has finished, and therefore you get a worst case execution overhead for the application B. And you can see that those services in the kernel do not overlap, which means the other processor has to wait until the other core has to wait until the core run on which application A is running is finished. In terms of the fine-grained locking, which has now been implemented, you can see that the cores are actually working in parallel and that the application A does not lock the resources when it is in the kernel. That means that the application B can execute its kernel safe services in parallel without any worst case execution addition. So the fine-grained locking impact is quite clear. It means that as long as you do not access any shared resources, there will be no multi-core induced conflicts inside the kernel. So let's look at the overview. So we talked about hardware-related issues and fixed them by cache partitioning. I did not go into the bandwidth monitoring because this is a very complex thing, and we will later see in the results from the Rapita tools that it is not really an issue if you follow the advice and set up the system according to CAS 32A regulations. In simplicity, very simple, if bandwidth monitoring is switched on, the access to memory and time of an application which does too much noise on the performance counter will be shut down and the critical application can continue undisturbed. On application side, we have to look at the architecture and make sure that only critical applications are running at the same time and that no shared resources being used. And on the operating system side, you can make sure that there is no interference when you use fine-grained locking. So what is the benefit? So with PikeOS 5.0, we can allow or enable our customers to build CAS 30TO compliant airborne systems up to Del A right now. And the preconditions are fine-grained logging, cache partitioning, well-thought user architecture. Of course, you still have to do the static and dynamic code analysis, and this is where Matt will jump in. And only the last resort is bandwidth monitoring.
Thank you very much, Oliver. So firstly, I want to introduce Rapita Systems to you all. Rapita provide tools and services mainly in the aerospace industry. You can see some of the customers that we have worked with in the past here. And you can also see from the word cloud some of the things that we focus on in this domain. Rapita was founded in 2004 as a spin-off from the University of York. We still have our headquarters in York in the United Kingdom, but we also have Rapita Systems Inc., which is based in Detroit, Michigan, serving the United States and North America and South America. And we also have customers throughout the world who we service through our distributor network. So today we're going to focus on our MAC 178 offering. So that stands for Multi-Core Avionics Certification for High Integrity DO-178C projects. MAC 178 is built on top of the Rapita Verification Suite. This is a set of tools for providing functional testing through the RapiTest tool, worst case execution time analysis through RapiTime, structural code coverage analysis through RapiCover, and visualization of operating system and task level interactions through the RapiTask tool. We also have a variety of engineering services to help our customers meet all of the requirements working in the aerospace industry. So Oliver's already mentioned some of the problems with working with multi-core systems. I'm going to focus on the timing analysis side of things. We say that single core verification certification is a solved problem. We say this because we've been through certification. We've helped our customers go through certification with single core systems, and that's been going on for a number of years now. However, multi-core embedded processors have been available on the market for some time, but these aren't being fully utilized in the aerospace sector currently. As far as I know, there is no one who's gone all the way through certification with the FAA or EASA with a multi-core solution where all the cores are active. Some of the reasons for this are that the processors themselves are extremely complicated. They're often in the form of a system on chip where there are multiple buses and multiple ways of the individual components on the chip interacting. There is what effectively amounts to a network being implemented inside the chip with packets being sent around. But mainly we're going to focus on the contention for shared resources. So a multi-core system on chip has multiple cores, but it doesn't have independent main memory and independent buses for all of the cores. So some of the resources are per core, such as the level 1 cache, but then you may have level 2 cache, level 3 cache, which is shared between cores. You have main memory and I/O buses that are shared between cores. And this means that what is happening on one core can affect the execution time of something happening on a different core. And this makes it very difficult to bound the overall execution time of the software. Also, with a multi-core system, the classical approach of static analysis for timing purposes is basically completely infeasible. The chips are simply too complicated to model to the required level of accuracy. And you have things such as temperature-dependent clock scaling, which is incredibly difficult to model. So there are mitigation strategies, which have been mentioned already, for addressing these interferences. The key thing is that these require verifying to make sure that they are working correctly. Another approach is to simply turn some of the cores off. That is something that is being done presently. Most of the extra certification required for multi-core systems does not apply for running single core on a multi-core SoC or running 2 cores in lockstep. But it is actually still important to verify that the other cores are not affecting the execution time. Recently, we've discovered that there is a difference between disabling calls altogether and enabling the calls but holding them in an infinite while loop. So we mentioned that robust mitigation strategies are required, and measurement-based analysis is required on the real hardware to get confidence that the strategies that we put in place are really working. All of this requires a strong ecosystem and cooperation between the various parties. At Rapita, we've worked with the SoC vendors to acquire in-depth technical information, and that's really important for identifying interference channels. Sometimes the interference channels are not obvious, so there are some obvious shared resources such as caches and access to main memory, but sometimes, for example, even with cache partitioning for shared caches, there are some common channels that all the cores go through. An example of this is the misstatus holding register, which all the cores need access to, even if their caches are already partitioned. We also work with the single board computer and board providers, as well as the operating system vendors such as SYSGO and the various middleware providers as well. So the RTOS offers these strategies for reducing interference. I wanted to emphasize that the interference it's never fully mitigated. There is no magic bullet to turn off multi-core interference. However, we don't require it to be fully mitigated. We really require a deterministic and predictable timing behavior that we can use to demonstrate the software executes within its timing bounds. There's also a sort of implicit goal here with a multi-core system. If you were to, for example, move from a single core system to a quad core system, you're never going to achieve a 4 times improvement in throughput. However, if you were only achieving a 1.1 times improvement in throughput, then the whole process could be called into question. So there is an implicit goal as well to achieve throughput and computing power that is significantly increased compared to running in single core configuration. So we need to confirm the mechanism is doing what we expect it to do, and we still need to confirm that the application, when assembled as a whole, is still meeting its deadlines, and more importantly, provide evidence to convince a third party that that's the case. We're talking here about DO-178C, which is the latest guidance for aerospace. Oliver mentioned earlier something called CAS32A. So CAS stands for the Computer Authority Software Team, and they produced some guidance for how to comply with DO-178C with a multi-core system. Note that DO-178C is still the master standard that you're certifying against, and CAS32A is a set of guidance for how to comply with DO-178C. As the CAS itself has been disbanded, the guidance in CAS32A has been rolled into a new publication called AMC 20-193. Also called AC 20-193 in the US. It's the same document under 2 different names there. And this inherited most of the content of CAS32A with some slight changes. We recently did a webinar discussing in detail the difference between CAS32A and AMC 20-193. So please get in touch if you're interested in this topic. But essentially, the document provides a whole series of activities that the applicant must comply with, or can comply with, to demonstrate that their system is safe and is certifiable for DO-178C. So the Rapita approach to this problem, which we call MAC 178, consists of 4 strings. Firstly, we have our core tooling. All the RVS tools run on single core systems and apply to single core certification, but they're also used also can be used in a multi-core context. We also have engineering services, and these range from integration services, integrating our tools into a software and hardware environments, but they also include helping to design, run and analyze multi-core timing tests and experiments. as well as identifying interference channels, as I mentioned earlier. We also have RapiDeamons, which is the first time we've mentioned that in this presentation. And the RapiDeamons are interference generators, and we'll talk about those in a little more detail later on. And finally, we have certification artifacts themselves, as in templates and technical reports that we can help our customers assemble in order to produce the evidence that gets submitted at the end of the certification process. So in terms of the RVS tool suite, the key starting point is the RapiTest tool, which enables you to build a test scenario, define what the inputs and configuration of the software is, and it will build a test harness automatically and execute those tests on target. The key thing with RapiTest has always been automating. In order to certify a multi-core system, there are a great number of experiments and data that needs to be collected. So automating all of this process so it can run without manual intervention is key to achieving certification with the minimum cost for the customer. RapiDeamons, as I mentioned, are the interference generating tools. They are small pieces of code that have been fine-tuned in order to generate the maximum possible interference per instruction executed. So they effectively represent the worst possible case of interference, and they are carefully tuned to both the particular interference channels, such as cache or main memory access, as well as the particular SoC or processor being used. And finally, because we are in the business of helping customers certify the software, the RapiDeamons are qualifiable, as is the RVS tool suite. Finally, we also have the RapiTime tool. You can measure interference directly, and in fact, our tools are able to gather performance counters, such as number of cache misses, etc. And that is one way of quantifying how much interference is happening. But the way that really matters is the effect on execution time, because that's what we're trying to prove, that our execution time is within certain bounds. So RapiTime is a tool for worst case execution time analysis. It works on target, and it's been specifically designed for safety critical embedded systems. It concentrates on the worst case timing behavior in contrast to other timing tools which only focus on the average case timing behavior. RapiTime works on single core systems, but it also works on multi-core systems as well. And so it makes the ideal tool for actually measuring what is the overall effect of interference on execution time itself. And finally, I wanted to outline the process in a bit more detail. We start with the platform characterization. So this is understanding the hardware itself and how it behaves. To start with, we would run the RapiDeamons in isolation. We can verify by looking at performance counters that the RapiDeamons are acting as intended. They are generating the types of interference that they are supposed to be doing. And we can verify the slowdown against a known piece of code. You can also baseline the application code at this point against the RapiDeamons in order to understand what is the worst case effect of interference on execution time. Secondly, there is an activity in software characterization, understanding the applications themselves. So we can fingerprint the applications using the data from the various RapiDeamons that target different interference channels. And that will tell you which parts of the application are sensitive to interference across which channels. Some parts may, for example, be I/O bound, interfering with or sensitive to interference across input-output channels. Some might be sensitive to their cache being used and cache eviction. Some might be sensitive to main memory bandwidth, things like that. And this helps plan and schedule the application so that competing parts of the application don't compete unnecessarily for resources. We can run the application as a whole against the RapiDeamons to verify what we're actually seeing in practice. And we can also verify the RTOS mitigation strategies and show that they are having the intended effect, and more importantly, that with the mitigations in place, the interference is within acceptable bounds. If you want any more detail about the process, please do get in touch. We also have an upcoming training session happening 26th to 27th of July in Huntsville in the United States. And we also have some resources that you can download. We have a multi-core white paper, and we have a more general white paper addressing DO-178C compliance as a whole. And if you have, again, any of the questions I mentioned, please do get in touch. Our email address is just here. And finally, we have a demonstration for you of the PikeOS interference mitigation strategies and the RVS tooling running on a real embedded multi-core system. In this demo, we will be examining the timing behavior of a critical application running on the NXP T2080, which is running the SYSGO PikeOS real-time operating system. Rapita Verification Suite will be used to specify tests and collect on-target timing metrics. Firstly, let's explore the PikeOS setup, which is defined in Codio, SYSGO's development environment for PikeOS. In the Project Explorer, we can see Proc1, which maps to our critical application, and the other three processes, which map to RapiDeamon contenders. Process 5 is our dummy non-critical application. Now, in the Rapita Verification Suite, we can see the integration we have set up for running timing tests and collecting timing data. Our tests are defined as JSON files, which you can see here. A new RVS feature scheduled to be released this year will allow you to use RapiTest's native test editor to build multi-core timing tests in a more visual way from the GUI. Let's take a quick look at the JSON file. Note the application of hardware event monitors that we want to measure, for example, L2 cache misses per thread. In our first scenario, we can see a baseline test with no contenders. In the other scenarios, you can observe a variety of different contenders running on each core. In Codio, we define that processes 2, 3, and 4 run on our spare cores, and our application of interest is running on core 0. You can define as many scenarios as you want to run different combinations of contenders and applications. In RVS, we have a number of configuration options available. In this instance, we are going to be using the metrics integration, which references the T2080 QDS integration. You can set up multiple integrations to easily switch between targets. For the run command, running on target, we are going to be using the Louterback Trace32 debugger to extract timing metrics. Depending on the metric entry that is added here, we will automatically generate the appropriate commands to be run in a CMM script. This script runs with Trace32 to set up the performance counter control registers in order to select the correct metrics to log. This means we don't need to produce any kind of kernel driver to do it for us in code, and only use what's available with the debugger. This approach ensures that we halt the target at a sensible point before we want to start recording the metrics information that we're interested in. The first PikeOS interference mitigation mechanism we are going to activate is L2 cache equipartitioning. PikeOS comes with a comprehensive platform manual which specifies how to use this technology. Back in Codio, you can see that L2 cache equipartitioning is now activated. The second mitigation strategy we are going to use to reduce interference is time partitioning. To demonstrate a system that does not have sensible time partitioning strategy in place, we have specified our critical application to run in the same time window as our RapiDeamon contenders. After that, our non-critical application runs on its own with no contention. For the purposes of comparison, we will now set up a more logical implementation of time partitioning. We will switch our critical and non-critical applications around so that our critical application now has its own dedicated time window. Our non-critical application that previously had its own time window now runs alongside the other contenders that represent other non-critical applications in a real system. You can see it's very simple to implement this change. Codio also makes it easy to see which core different time partitions are assigned to. The red box around the first item indicates that it is the synchronization core, so that is the master core that everything else is synced around. Now that we have specified our tests and set up our interference mechanisms, we can return to RVS to collect real on-target timing metrics. We have selected a number of different instrumentation profiles and entry and exit points. We have finished our preparation stage, so now let's run our build. This will load our build onto the target, run it, and collect and process the trace. it will be repeated for all of the test scenarios we defined earlier in the JSON file. If we open up the Lauterbach Trace32 Power View, we can observe one of the test runs taking place. It will then let the target boot up into U-boot, download the PikeOS image and do any other metrics capture configuration, and then instruct the target to run for the length of the test. We set a breakpoint on one of the RVS library functions which gets injected, called RVS output. When it hits this, the target will stop running, and then we'll be able to export the data from Trace32, which will appear in the trace list window. In order to capture the metrics information and timing information, we are actually doing a data write trace via the Nexus port on this particular board. That information is exported in binary format. We post-process the trace to convert it into the native format for RVS, which is a compressed trace file called an RPZ. After that, we can import the timing results into RVS. On the left-hand side of the screen, you can see the baseline test results where no PikeOS mitigation mechanisms were used. On the right-hand side are the results from the same tests, but with both L2 equipartitioning and an improved time partitioning profile in place. We can see that without the mitigation strategies, when we're running our final set of contenders, there is a very large increase in the execution time of our critical application. In contrast, the results on the right, where mitigation mechanisms are enabled, show a much more consistent execution time. There is still a slight increase, but it's a lot more consistent, and that will be a lot more predictable. If we click into RapiTime's Metrics tab, we can observe the results from our hardware event monitors that we specified in the JSON test file. We can use the filter feature to compare these metrics with and without RapiDeamon contenders present for both the left and the right-hand side results. We can then sort by metric so that they're all in sequence. The first entry of each set is the one without any contention. The entries below each event monitor are for the tests that did run contenders on other cores. For example, we can see the large increase on the final test scenario of 155% with contenders running compared to the baseline with no RapiDeamon contenders. Let's repeat the process on the right-hand side for the results that include PikeOS mitigation mechanisms. We can see that with both our mitigation strategies in place, we only get a 4.6% increase in execution time. Please note that PikeOS has other interference mitigation mechanisms, including bandwidth allocation management and fine-grained blocking, which are not explored in this demonstration.
Okay, I think that just about finishes things here. Thank you very much indeed for everyone for attending. If you want to find out more information, visit either SYSGO's website or Rapita's website. Also, info@sysgo.com will get you in touch with the SYSGO folk, and info@rapitasystems.com will do the same for the Rapita contact you might need to speak to. Beyond that, we do a lot of webinars. Please do check our website and social media accounts to stay up to date. And until then, thank you very much for attending. Thanks to the presenters today, and we'll see you next time.
Thank you. Goodbye for now.
Bye.